Let's go over midterm 1 from spring 2021. We have data on CDC weekly deaths. Let's connect to that data. I downloaded them from Nexus. They came to my downloads folder. Here's CDC weekly deaths. Let's take a look at the fields that we have. We have a jurisdiction, which looks like a state. We have age group, and we have different dates, years corresponding to that date, and number of deaths. Well, let's take a look at how many observations we have. 8,581. Let's figure out what's the unit of observation. So it clearly looks like it's going to be jurisdiction or state, but for each state we have lots of observations. So it's probably going to be also broken down by date, not just year, but probably all the way down to an actual specific date. And on each day for each state we actually have 6 observations, and that probably means that each of those 6 observations are for different age groups. And yes, indeed, so for every date, for every week, we have one observation for each age group. When I look at the number of rows in this table, it equals to the number of observations, 8,581. So the unit of observation is jurisdiction, date, and age group. Fantastic. Create a time plot showing weekly deaths in the US between 2015, 2020, and so on. Okay, perfect. Let's do that on the next sheet. So we're going to put date on the horizontal axis, and we're going to put a number of deaths on the vertical axis. We want not aggregates by year, but we actually want it by weeks. So the original granularity of the data. So let's use a continuous axis here, plot actual date. We have about 60,000 deaths, about between 60 and 70,000 deaths every week. Fantastic. Let's add average line to the table. Yes, on average about 55,000 deaths. We clearly see a seasonal pattern. In winter months, deaths tend to be higher than in the summer months, and of course in March 2020, we see market increase in the number of deaths due to the pandemic. All right, fantastic. So that's question number 2. In question 3, we're supposed to create the same thing. So let's actually duplicate this slide, but make a separate line for each age category. So let's just drag the dimension of age onto color. You can actually get rid of the average line, and now we have 6 separate lines, one for each age category. What do we see? Well, clearly the sum of these lines adds up to the blue line from the previous graph. We see that deaths, number of deaths are highest for the oldest age group. That makes sense. It's lowest for the youngest age group. We also see that the seasonality is really most pronounced for the older group. The deaths for the younger groups seem pretty stable over the course of the year, but we actually notice a big pickup in deaths in 2020, even in some of these younger categories. So COVID clearly affected not just the elderly, but also middle-aged and young people. All right, that's question 3. And question 4, we are supposed to do, let's take a look, create a vertical bar showing the number of deaths by age group in the US and so on. Okay, so let's number of deaths by age group. So I'm going to put age group on columns, number of deaths on rows. I want to sort it so that the bars are sorted in the age of each group. So I'm going to put under 25 years old right before 25 to 44-year-olds. And actually, that makes sense that the number of deaths over the course of those 5 years, well, actually 6 years, is the highest for the eldest age group, slowest for the youngest group. In terms of magnitudes, this clearly is a much bigger number. Here we have a number of deaths of 85-year-olds, around 5.6 million. What we see in the previous chart are numbers around 17,000, but those are weekly numbers. So if we add up 17,000 times 52 weeks times 6 years, we get about 5.5 million. Okay, so those two numbers are consistent. Fantastic. Let's go to the next question. We are supposed to create a highlight table showing the percent change in the number of deaths for each age group. Percent change, okay. Annual number of deaths. So let's do that. Let's first create a table where we have different age groups in rows. Let's put year. Actually, let's use this year. Let's make it discrete. And let's put it on the columns. And let's put number of deaths in the table. And so now we see the number of deaths for each age group. And let's actually, again, sort it so that we have the under 25-year-olds, above 25 to 44-year-olds. And so we see the number of deaths for each age group in each year. But what I want is a percent change from year to year. So that's a table calculation where it's going to be percent difference from table across, because we have years across. And let's keep it this way. We're supposed to do a highlight table. So we want that number of deaths to be mapped to color, not just the number of deaths, but the number of deaths, not count. So number of deaths, it's going to be mapped to color, and using the same table calculation, which is a percent difference from across table. And let's make the mark square so that it's a highlight table. Let's edit the colors so that we have about diverging red to green. And let's make it reverse so that increase in deaths is red, bad, and decrease in deaths is good. So we can center it at 0. That's perfect. Okay, so what we see is that clearly in 2020 we see increase in deaths across the board. We can certainly add column totals. So we, oops, why did it do it this way? Oh, yep, there it is. So we can see that in 2020, deaths actually increased 20%, which is unprecedented. It hasn't happened in any other year across age groups. In the highest is actually the middle-aged, 25 to 44 years old, that they had the highest percentage increase in number of deaths from year to year. Okay, pretty disturbing, pretty stark evidence of the effect of COVID. All right, well, let's explore this a little more. I created a dimension that shows the season of the week. Yes, winter for December and January and February, okay, and so on. So there are different ways we could do this, but we're going to be creating a calculated field. And so what's the best way of doing this? I think we can we could certainly take our week ending date and create a group and group all these dates into winter weeks and summer, spring, and fall weeks, but that's a little laborious. So let's create a helper field. Let's create a field that we can call month. And we've used this function before, month out of a date. We're going to extract a month out of a date, out of the date of the week. So we'll say OK to that. And let's see if we can create group from this. Oh, that's not bad. We've got January. All right, January and February. That's going to be grouped into winter. And actually, we're going to add January to it as well. And we're going to add December to winter as well. Okay, and then we got March, April, May is spring, and June, July, and August is summer, and September, October, November are, of course, fall. Fantastic. Perfect. So we got this dimension that is season. And I believe we're supposed to create a bar chart by seasons in number of deaths. And indeed, the number of deaths is highest in winter, which is not surprising given the time plot that we saw earlier. Okay, in the next question, we're supposed to see if the pattern, if the seasonal pattern of deaths varies across different age groups. So let's put months again on columns. Let's put the age group on rows, and let's put number of deaths inside the table. But this time, let's see what percentage of deaths for each age group happens in different seasons. So let's do another table calculation. This time, we're going to do percent of total, and we're going to do percent of total across the table. Which means the percentages will add up to 100 across the table. So for each group, we'll know what percentage of deaths for that group happened in each season. Okay, and we can certainly make this colorful as well, so that we can really see where the deaths happen. We didn't have to do that, but let's also make sure that we put our 25-year-olds above 25 to 44-year-olds, and let's see. Actually, it looks like there's a pattern here. We see that winter is indeed really bad for the older age groups, but it's not as bad for the younger age groups. For example, for the 25-year-olds, summer is actually the worst month, and winter is not that bad. So clearly, differences across age group, which, when you think about it, perhaps makes sense. The elderly are more susceptible to flus, whereas maybe in the summer, the younger people are traveling, driving cars, doing crazy things, who knows. But clearly, this is a pattern that we see clearly in the data. Next, let's examine the timing. Oh, so we already did that. Now we're supposed to join some data. So we got some data on the state populations from 1960 to 2020. Annual data on state populations, downloaded and join it with the CDC data. So let's do that. Sure, I'm going to open a new sheet, but I actually need to go to the data source. I need to open this table of CDC weekly deaths, and to it, I will join my population table. So it's in my downloads folder, population. There is a state population 19 60 to 2020. So let's drag it into the canvas, and now let's think about how we should join them. So, so the grain of the CDC data is weak state age group, and so we certainly need to take into account the state and timing, date. We actually have a year in the CDC data, and that probably should be lined up with year in the population data, because the population data looks like annual data. And so now joining it on year and year is going to line up the years correctly. But there's also another dimension that exists in both data sets, and that is jurisdiction. That's called jurisdiction in the CDC data. It's called a state in the state population data. So let's see, let's take jurisdiction. So that it was mostly, it looked like mostly states. We see Alaska, we see down here probably Alabama, and so on, and that should be lined up with a state in the state population data. And so we are also told that we want to keep all of the CDC data. So we want to choose a left join, because that's going to keep all of the CDC data, even if the CDC data has some jurisdictions that are not present in the state population data. And so this actually looks okay. And so, but we have to keep in mind that the grain of the CDC data is not just a state and week, but also age group. So if I'm looking at let's see, this population varies by state and by year in the state population data, but that population is going to be constant across different age groups, because I don't have a population for each age group. I just have the total state population. Okay, so so that's how we can join the data. Let's see if we lost any observations. We didn't. That's good, because we used the left join, so we shouldn't lose any observations. But let's see if all the jurisdictions are that we see in the CDC data also line up with the state data. So we see Alabama, Alaska, they're all there. They're all there. As Puerto Rico, we actually don't have anything, any data, any population data. If I put population in here, any population data for Puerto Rico, right? Because there's no state corresponding to Puerto Rico. So Puerto Rico is in the CDC data, but not in the state population data file. Okay, fantastic. So the next, we're supposed to, in question 9, create a scatter plot to see how the number of deaths is related to state population. And we're supposed to do this by state and by year, so that we have 306 marks, 6 years times 51 states, or 51 jurisdictions, 50 states plus District of Columbia. And we're asked to see if any years stand out. So we're going to put year on color. clearly there's a positive relationship between population and the number of deaths. Notice the axis on the population. So what we're plotting here is actually a sum of population, but we're summing population across 52 weeks and across different age categories, right? So for each state and year, we have only one population number that's repeated 52 times for each age category. So it's 52 times 6 age categories, a lot of times. And that's why now it says population is like 13 billion for California. Of course, California doesn't have 14 billion people, but that's because we're adding up population multiple times. So we could change the method of aggregation to average, or even if we choose a median or minimum and maximum, then we would have an accurate population count. And so indeed, California has about 39 million people. And indeed, year 2020 in yellow stands out. That for a given population, it's always the highest dot with the most deaths. Okay, so that makes all sense. Finally, we're supposed to focus on 2020 and focus on the 5 largest states. So let's put some filters for states. Let's do top, I believe we said top 5 states by, was it by average population? So we could do it by population average. So it's going to really average it across different years. And we can see what states these are. California, Florida, New York, Pennsylvania, that makes sense. We're supposed to also focus on year 2020. So sure, we can add that to the filter. Now we're supposed to show deaths per 100,000 people, a time plot. So I'm gonna have date on columns. I'm gonna again make it continuous. Oops, not a week number. Oh, sure, I could make it week number. That's fine. Or I could make it a date. I like that better. And so I don't want to plot just number of deaths, right? I could do that, and I could do that for each different line for each state. And this actually looks familiar. In New York was hit hardest, and in the spring, COVID came later to the southern states, Florida, Texas, but Pennsylvania and New York felt it in the spring. But I don't want to show the number of deaths. I actually want to show a number of deaths per 100,000 people, right? Because some states are bigger than others. I mean, these are all 4 big states, but there's a big difference between California and even New York. So whenever we see COVID data, we always see them scaled by population. So here we're going to scale these number of deaths by state populations as well to calculate death rate. So what? How can we do that? So I'm going to create calculated field. I'm going to call it deaths per 100,000 people. And so we're going to add up deaths, number of deaths, and then we're going to divide that. And now we have to think about what do we divide it by. Now, if we divide it by the sum of population, then we might have a problem, because we'd be summing population again across different age groups and across different weeks, although now we have just one mark for each week, but we would be summing population across 6 different age groups, and we don't want that. We don't want to divide it by 6 times population. We want to divide it by population. So instead of dividing it by sum of the number of deaths, we're going to divide it by the average of, not number of deaths, by the average of population. And we're going to multiply it by 100,000. So that it is number of deaths per 100,000 people. So we're going to say okay to that, and we're going to replace this aggregate measure by we're going to replace some of the number of deaths with the aggregate measure with the death rate. And so we see that the number of deaths per 100,000 people in New York was still very high, but now we see California, and California deaths are not as high because we scaled it by very large California population. So that blue line for California is no longer at the top. It's now much lower because we scaled it by population. Okay, so this is midterm 1 in spring 2021. And I'm gonna stop here.